So let's take a look at our last chapter, chapter 10, on acids and bases. There's a lot of material to cover, so I'm not going to waste any time on the table of contents. Historically speaking, concepts concerning acids and bases have been around for quite a while. The first useful one was proposed by this Swedish scientist, Arrhenius. And his idea of an acid versus a base, and by the way, for the longest time, we could actually taste stuff in the lab. That was kind of stupid, wasn't it? Yeah. But if we go to food and medicines, lots of foods taste sour. There's your acid. Acids are sour. Bases are bitter. And it's hard to find a food that you want to eat that's bitter. So I turned to medicine. Lots of medicines, if you break the capsule for some reason, you get some of the actual compound on your tongue, most of them will be bitter. They're bases. And the reason they're bases, I'll just give you a short idea there. The reason they're bases is that most of them are insoluble in water. So in order to get them to solubilize in your system, you have two choices. You can either hit them with strong acid. So you see, sometimes you'll see the name of the compound, and then you'll have this after it. They've hit it with acid to make it soluble in water. Sometimes there will be, actually, they don't ever put the base on the end, but they can add a strong base to it. And it depends on the structure of the molecule as to which one you use. But a lot of them are basic and they taste bitter. I try to give medicines to my dog sometime, and it must have been really nasty because they foam at the mouth and spit it out. So I thank God for pill pockets. You know, pill pockets?
Yeah. They're like little treats in this.
Oh yeah, the real squishy, tasty treats, and they got a hole in the middle, and you stick your pill in there and squish it, and feed it to them, and they down it goes.
I don't want to know. My dog actually was. She's a dopey. Pain pills. She takes out like nothing. I'm like, you don't.
What breed is this?
She's a pit bull.
Oh.
She has hip dysplasia. She's born with it, so she has to give medication.
That's terrible.
Yeah.
I got a dog at home with lung cancer.
Oh.
She seems to respond to prednisone. It's easier for her to breathe.
Yeah.
So I figure she's 14 and a half, and you know, it's like any grandparent, you know, if they're up in their 80s and they want to do something, let them do it.
Yeah, that's how with one of our dogs. He's 12, I'll be 13, and we just let him do his own thing.
Yeah.
My cat's just not chewing up its food very well.
Oh.
So we're giving her wet food.
Okay.
Could be missing.
Well, I had a vet tell me one time that it's good to have at least a mix of wet and dry, because cats for some reason don't drink enough water.
No, they don't.
And they dehydrate easily. So giving them a little wet food, be sure that they get some water in there.
Or the sink. She loves the sink.
The sink.
The sink. Oh.
I got a couple that like to drink out of the faucet. Yeah. At least they don't drink out of the toilet.
Oh, God, I hate that. It's on the toilet, and the toilet's all wet.
Okay, back to acids and bases. Arrhenius' idea of an acid was a molecule that had a hydrogen in it, right? We've gone through this nomenclature thing. So an acid's going to have a hydrogen, at least one hydrogen, and then some other part of the molecule. Right? So you can have 1, 2, 3 usually. I've never seen 4 or 5 in this arrangement. So that's an acid by Arrhenius' definition, and a base has a hydroxyl on it. And when you put it in solution, the acid dissociates into its protons plus what's left over. Okay, so this This is what causes the acidic, the bitter, the sour taste. The base dissociates into that with the hydroxyl. See, I'm still picking it up. So I'm not sure if Arrhenius understood what was happening when you put acids and bases together, but eventually, if you put these two types of acids and bases, this covers most of them, then you get a reaction between the hydrogen and the hydroxyl. Right? And that always gives you water. Okay. What's left over? This B plus and that A minus. I have to write them in cation, anion order. And this is called in chemical terms a salt. So it doesn't have to be sodium and chlorine to be a salt. In chemical terms, the product of an acid-base reaction is water and a salt. So I'm getting a little ahead of myself here. So this worked for a long time. Hold on a second. I'm just checking to see. Yeah, we're going to get to it in a minute. Okay. The process that either of these undergoes is a little bit different. For acids, we call this ionization. In other words, the association of the proton and the anion part of the molecule is more electrostatic. So all it has to do is just break off that proton. So they become ions. For the base, it's a little bit different. This association is more, I guess you would call it covalent, but it's not so much so that when you put it in water, then the hydroxyl dissociates from the cation. It's a fine distinction, I understand, but nevertheless true. So just, if you need to, just memorize acids ionize and bases dissociate. All right. So this works for most acids, bases. That came out of your book, I'm sure. Just shows you the same thing I put on the board. So we won't spend a lot of time there. This is just a review, right? Acid produces hydrogen ions, bases produce hydroxyls in water. Now that's still true, even if we have to modify it for odd molecules, those that do not have hydroxyls in their structure. So it makes you wonder, all right, if it's basic, where's the hydroxyl come from? So we're going to figure that one out. Then along comes, 40, 45 years later, these two scientists independently, Bronsted from Denmark and Lowry from England, came up with an alternate definition. What they're saying, they focused on the protons only. So an acid is a proton donor. In other words, it gives up a proton to something else. And a base is a proton acceptor. Okay, so, and that actually, that definition works better than Arrhenius's definition.
So it's kind of like a negative blood, no positive blood.
I guess.
One can give, and then one cannot give and just accept.
Okay, yeah, that's a good analogy. Okay, so why do we need this definition? Well, I'm going to give you an example of one where the base doesn't have hydroxyl in it, and that's ammonia. Right? Ammonia, pure ammonia, is a gas at room temperature and 1 atmosphere pressure. But when you dissolve it in water, make it aqueous, okay, it produces a basic solution. And we can measure that with various means, indicators, color indicators, like little strips of paper put in there, litmus paper. or you can use a pH meter, or you can put a few drops of phenolphthalein would be a good one because it'll turn bright pink in the basic solution. So we got to explain, why does that make a basic solution if our focus is on hydroxyls? We don't have to lose that focus. We have to explain where it comes from, though. So when you put ammonia in water, what happens is the ammonia reacts with water. Right? Water. Now ammonia is a proton acceptor. It's a base. It accepts a proton from water. So let's see, I don't want to go off the board. So when it accepts that proton, it makes the ammonium ion. We've studied that one before. What's left over? Okay, so there's where the hydroxyl comes from that reaction. So Bronsted and Lauer's definition is actually necessary to explain these types of acid-base producers. Now, as it turns out, oh, and let's see. If we get to the lab today or next week, you're going to be using a concentrated version of this material. And it will say on the side, probably this, ammonium hydroxide on the bottom. Okay, so if your method says use ammonia solution, look for this one. Okay. All right. So now we have a Bronsted-Lowry definition that works for the Arrhenius was maybe 95% of the possibilities. Bronsted-Lowry is over 99% of the materials that give you acid and base solutions are covered by their definition. Just focusing on the proton. Okay. So if we put an acid in solution and we follow Bronsted and Lowry's definition, in this case, hydrofluoric acid reacts with water and transfers a proton to the water molecule. So that makes hydrofluoric acid and acid by proton donation, and water is the base. So water being the base, now it produces this special ion here. We call it the hydronium ion. And this is actually what happens in solution. This reaction, when you put an acid in solution, it transfers a proton to water. Sometimes we write reactions like this. Right? This aqueous solution produces that plus that in solution. But that's a shorthand version. That's not what actually happens. You don't have independent, free-floating protons in aqueous solution. They're always attached to a water molecule like this. But when we get, if we have to do any calculations, if we have to do any stoichiometry or anything like this, this works just as well as that. Okay, that's why we do it, because it's simple. But this is reality. Okay, so what we produced, if we stick to Bronsted and Lowry, their definition, now we've produced, from this acid, we've produced a proton donor, we've produced a proton acceptor in the fluoride ion. So now it's a base, and we call it the conjugate base of that acid. And you'll notice two things about conjugate bases and the acids they come from. First of all, it's only missing one proton. Okay? If there are two protons or three protons, it only loses one at a time. For instance, sulfuric acid. Right? When we put that in solution, it'll lose one proton and leave us with that part of the molecule. It still has a hydrogen that's available. Okay? So we could go ahead, they happen in sequence. So we could take this one, and it would lose a proton to some other molecule and leave us with that one, the sulfate ion. Okay, so it happens in steps. This is the conjugate base of that acid, but now it becomes the acid, and this is the conjugate base of that acid. Simply because it lost a proton. By Bronsted and Lauer's definition, it's an acid. And the acceptor, the base, becomes a conjugate acid. Now it has a proton that it can donate. Okay? All right. So let's carry on. Okay, when we talk about a conjugate acid-base pair, that's what we're focusing on. The acid and the base are related in two ways. They have the core, HF, this would be the core right here. And then they have the loss of one proton to go from acid to base. Those two must be met to be a conjugate acid-base pair. So in this case, well, the possibilities are, this could be an acid and that's, well, now this is the conjugate acid of that base. So the acid-base pair would be this acid and that base. So where are we? Here, right there. HF and F minus are the acid-base pair. Okay? All right. Now, that leads us to a discussion of water. Water's kind of, well, actually, water's not the only molecule that'll do this, but it's the most important one for our work because everything we're dealing with is an aqueous solution. Right? Even most of your tests, any of your chemical tests or non-chemical tests, probably involve water in some form or fashion. And water has a particular behavior that is not unique, but is necessary to understand. In pure water, right, when you only have water molecules, there's no reason why they can't react with one another. Right? And they do. This proton transfer to that one leaves us with this one plus hydronium. Okay. The fancy word for that, well, actually, there are two of them. It could be called amphoteric or amphiprotic. Amphi means both. It's a Greek prefix, it means both. So water could be either by both an acid and a base. But they can't be the same acid base at the same time, right? This molecule is the acid because it transfers the proton to this molecule, which is the base. So now this is the conjugate base of that acid, and this is the conjugate acid of that base. And this is, in pure water, this is going on all the time. But have we talked about equilibrium a little bit? Okay. So it can go both directions, but it likes to be over here more than over the other way. Right? So maybe it's a little bit this way and it's a great big this way. Most of it's over here, just a little bit over here. I should have my hold on just a second. I need my hard copy. Nope, wrong one. Here we go. Okay. Yeah, we're going to talk about it, I think, in just a second. All right, did we talk about the equilibrium constant? How to calculate the equilibrium constant?
No, I don't.
We didn't do that one yet. Okay. Well, I'll leave that for, I'm gonna have to eventually, so we'll not introduce it just yet. So any substance that can either lose or accept a proton is amphiprotic or amphoteric. And water is a good example of that. Other molecules can do it too. It just depends on their environment. Do they want to give up a proton more strongly than the other thing does? Or does it want to give up a proton more strongly than they do, then they're obliged to accept it? Okay. So different types of acid, we identify them as, in terms of the ability, how many protons can they give up in a sequence of reactions? If they only have one proton to give up, then they're monoprotic. And examples of that are, let's see. We're not going to give examples. We did this one just a minute ago. HCl, HNO3, nitric acid, hydrochloric acid, hydrofluoric. They only have one proton to give up. They're monoprotic. And the other example was H2SO4, sulfuric acid. It has two protons that it can give up. So it's diprotic. You could say triprotic. Example, phosphoric acid. Right? They put that in lots of drinks and foods, especially soft drinks, phosphoric acid. If you take Coca-Cola, a can or a bottle of Coca-Cola and drop a nail in it, in about a week it'll be gone. It's not just the acidity that does it. It's the reaction with the phosphate that's in the drink. So we can have three protons, triprotic, or you could just lump the di and the tri and any others together and call them polyprotic. And that covers all your bases. Poly just means many. Actually, there are some organic molecules that do have 5, 6, 7, 8 protons available. Okay. So the concept of strong versus weak. When we talk about a strong acid, we talk about the ability of the molecule to give up all of its protons very readily. It wants to get rid of everything it has. So when it reacts, let's do this properly. Hydrochloric acid plus water. It wants to transfer every proton it has. All the whole HCl molecules want to give up that proton. So it produces this one plus that one. And it's almost exclusively this direction. In fact, for our purposes, you can say every one of these converts to that. That's a strong acid, okay? In chemical terms. The tendency is to view strong versus weak as which one can cause damage to your skin, like which one's corrosive. We can contrast this with a weak acid, like acetic acid. So it would, I'm going to write this in shorthand version. Right? So there's the acetate ion derived from this molecule, acetic acid. And you know acetic acid intimately. Vinegar. Okay. This one prefers, goes a little bit this way, goes way back that way. It prefers to be that. Right, so that's a weak acid. It only gives up just a small amount of hydrogens transferred to the water molecule or whatever else is in the solution. That's a weak acid in chemical terms. Okay. where I was going with this was our understanding of strong and weak in terms of corrosivity. Right? A strong acid can be corrosive if it's concentrated enough. A weak acid can be corrosive if it's strong enough. We used to buy this material, acetic acid, for the laboratory. We call it glacial acetic acid. It's 100% pure. And you don't want to get that on your skin, because even though it's a weak acid in chemical terms, it produces enough of these at that concentration that can do some damage. Okay. So there's a difference between the chemical understanding of strong and weak and OSHA's understanding of corrosive. Okay. And you can have such a weak solution of hydrochloric acid that you can drink it. You just make it weak enough. Lower the concentration way down. Well, think about it. What's the first thing your food encounters? Well, actually, that's not true. First thing your food encounters when you eat it is your saliva. And it has an enzyme in there called amylase. It starts breaking down starches. But once it gets past that, then on the way in the stomach, it encounters hydrochloric acid at about between pH 1 and 2. And I haven't defined pH yet, but I will. It's concentrated enough to start breaking down your food. Right? And your stomach is designed to not be corroded by that acid. If there's damage to the lining of the stomach, then you develop ulcers. And the acid that's there is part of the problem, because your protective mechanisms are broken down. That can happen with some anti-inflammatory drugs. They suppress your protective mechanism for your stomach. And then you develop gastritis at the least, and sometimes ulcers.
I know one of the women that I know, her horse has ulcers in his stomach go bad, her horse. And she has to give him some kind of special, I don't know if it was a supplement or something to help with them.
Yeah.
But he gets them bad.
Yeah.
I guess it has to do with something like that. I don't
It
know.
could be genetic predisposition too. Yeah. And the difference between ungulates and ruminants.
I don't know what that is.
Oh, ruminant, they're like cows and goats and sheep.
Oh,
They have multi-chambered stomach, right? One stomach, the rumen, the first thing that goes in there is at a certain pH. It's more basic, and it's more hospitable to microorganisms that help break down food. And then it transfers there over to the abomasum, I think, which is more acidic. Okay. And horses only have one stomach. They're like us.
yeah.
So that's why when they eat lots of food, and they do eat lots of food,
That's all they
it's
do.
more expensive to keep horses because they don't use their food as efficiently as cattle do. And horse poop is pretty solid because of all the stuff that they can't digest. There's some, I've heard it said that some of the digestion takes place in what we would call the appendix. And their appendix is actually useful. They have some digestion down there. Anyway, back to chemistry. These are some common strong acids. I mentioned hydrochloric and these halogens, chlorine, bromine, iodine, they produce strong acids. Strangely enough, HF is a weak acid. It doesn't like to give up its hydrogen very well. There's a reason for that, but that would take too long to describe right now. I'd have to give you some background, so we're going to let that go. The strong acids, the other members of its family, chlorine, bromine, iodine, they produce strong acids. Nitric acid is strong. Chloric acid, and actually stronger than that, perchloric acid. It just has one more oxygen here. Perchloric is even stronger than chloric. Oh, there it is. You read my own list. Perchloric is extremely strong acid. Plus, it's a very strong oxidizer. There are two different effects that are seen there. The acidity and the effect of this molecule on biological material. I used to use that day in and day out in the laboratory to digest plant material, to get rid of the organic fraction so I could get at the minerals. And you had to take some precautions with it. If we used concentrated, reasonably concentrated, about 70%. But if you put that directly on organic matter and start heating it up, you're likely to get a fire and explosion. It's that strong an oxidizer. So we would treat it first with nitric and let it sit overnight, the organic material, a pre-digestion. Then we could add this the next day and heat it up. We're perfectly safe. A guaranteed explosion, a nice big chunk of butter in a beaker, and then fill it up with perchloric acid and put it on the hot plate under your hood. Turn the heat up, pull the sash down, and evacuate the building.
Why butter?
Because it's organic.
No.
Organics and strong oxidizers, it will explode. If you think about it, most common high explosives have built into them some organic structure plus an oxidizer to go with it. Some of them have this, both in the same molecule. But that's another discussion. Sulfuric acid, that's a strong acid too. And there are others. Actually, phosphoric acid is not a strong acid, not even for the first proton. So its effect is problematic if the concentration is high enough. Let's see, any farmers in the family? No. There's a product that farmers can use. They have steel gates. And over time, the paint will flake off and in the sun will just and expose the underneath the metal to the air and moisture and start to rust. So you need to repaint your gate. You don't want to paint over rust because the paint won't stick to it. It'll just flake off and keep rusting. So you want to convert that rust to something that's more stable. And they have this pasty stuff. I think last time I saw it was green colored. It's kind of like a paint. And you wear gloves because it's very concentrated phosphoric acid. And you paint it on your gate. And it takes that rust and converts the iron oxide, which is rust, into iron phosphate, which is more stable and sticky to paint. And you don't even have to scrape it off. It just converts to that compound, and then you paint over it. But it's very high concentration. Even though it's a weak acid, it's still very effective in, well, it does the same thing to the rust as Coca-Cola does to that nail. It converts the nail iron to iron phosphate in your drink. So you don't want to drink it after you put a nail in it. Probably wouldn't taste good anyway. Okay, weak acids produce very little of this and mostly this. The equilibrium position is far to the left over here. That's a weak acid, chemically speaking. So this is your author's idea of an explanation. When you put this acid in water, you get mostly that. You get the A- part and you get the hydronium ion. If you do the same thing with a weak acid, you end up with mostly this still and just a little bit of this. Very, very small amount of proton transfer at equilibrium. Okay, strong bases. Bases, we define bases as those that dissociate if they have hydroxyl built in. Then these are the ones that the hydroxides that are strong bases. All the group ones, right? The first column on the left, the alkali metals, they make strong bases. Lithium hydroxide, sodium hydroxide, that is probably the most common industrial chemical in this country anyway, sodium hydroxide. And they produce it by taking table salt, sodium chloride, and driving a strong direct current through it. It separates the sodium out, the chlorine out as a gas. Then they take the two, take the chlorine, actually they take both of them. Take the sodium and dissolve it in water, make sodium hydroxide. And they take the chlorine and bubble it through sodium hydroxide solution to make bleach, sodium hypochlorite. But these are all strong bases, all of them. For the hydroxides of the second group, the alkaline earths, beryllium and magnesium are not strong bases. Okay, but the third one, calcium hydroxide, strontium, barium on down, those are strong bases. Now there's a caveat to that definition, because these hydroxides are not very soluble in water. So they're mostly solid, but whatever goes into solution dissociates into calcium and hydroxide ions, or strontium and hydroxide, or barium and hydroxide. They're not very soluble in water, but by chemical definition, they are strong bases because whatever makes it into solution dissociates. Okay. I know that's technical, but it's the truth. Okay. Which one of these following reactions would correctly represent a strong acid when placed in water? Strong acids have to show large dissociation. So we would say the arrow from left to right here in this case describes the dissociation. So it's going to be B. And it's supposed to turn red. That brings up another thought. For the lab, if we get to it today or next week, we're going to describe equilibrium processes. That's Le Chatelier's principle. And I'll define that for you later. When you're describing whether a reaction favors moving to the right or to the left, that doesn't mean anything unless you're referencing an equation. Because we could write that equation backwards. And then if you say it moves to the right, you'd be wrong. Okay, so whenever you say left and right, you need to reference an equation. Okay, or you could say it favors producing such and such or such and such. That would be valid. But if you're going to say left and right, you've got to reference an equation. Okay. All right. Equilibrium. This is in reference to acid ionization. But the equilibrium constant can work for any balanced equation. You can have forward and backwards reactions. So I'm going to write it this way. If we have the coefficient little a and then a compound or the element, whatever the case may be, and we react that with B, then it can produce maybe C and maybe D. See if that's still showing. Just a little bit. Right there, I think. Yeah. Okay, written this way, the equilibrium constant, and that's exactly what it is. It is a constant at a given temperature. Change the temperature, then the calculation changes. But as long as the temperature is constant, then the equilibrium value, this K value, is constant. And it's based upon concentrations at the equilibrium position. In other words, if we put A and B together in a closed container, and let them react, they will start producing C and D. Okay, so you're not going to get any reaction this direction right away because you're starting out with these and there's nothing over here. Okay? But as you start to build up some of these, then you get the possibility for those to react and go backwards. That's basic to the concept of equilibrium. And at some point, the rate of this direction equals the rate of that direction. Okay, so on a macroscopic scale, from outside, we may see this produced more and more and more. But at some point, we get to a point where if we measure this one, this one, this one, and this one, they stop changing. We don't see any change at all. But on the microscopic level, the reaction forward and reverse is furiously fast. It's just steamrolling through both directions. But since the rates forward and reverse are exactly equal, from the outside, we don't see any difference. Okay, so at that point, you have equilibrium. And the expression for equilibrium for a reaction like this is we take the concentrations of these and we put them in the numerator. And we use a square bracket. That denotes, by convention, that's the equilibrium concentration. Say molarity, 1 molar, half molar, 1,000th molar, whatever the case may be, goes there. Okay, and then from the balanced equation, we take the coefficients and those become the powers. So we take this one to the little c power and this one to the little d power. So you have to have a balanced equation to write this expression. And then we put the reactants in the denominator. And of course, with their coefficients. And that's equal to the equilibrium constant. Okay? So from this expression, we can say several things about that equation. See, since the numerator is an expression of the products and the denominator is an expression of the reactants, if this number is very, very large, like 10,000 or 100,000 or whatever, then we know that it's mostly here because that's the numerator. It's really big. If it's really small, it's like 10 to the minus 4th or 5th, 10 to the minus 10th, whatever, then we know that this one is the big one. And the reaction prefers at that temperature to be over here. Okay. Now, specific to acid ionization, this subscript here, by convention, if we say this with a little a, that's referencing the dissociation, ionization constant for an acid. And in that case, we write it this way. We have acid combining with water to produce the hydronium ion and this conjugate base of the acid. Okay, so these two go in the numerator, and then you would expect to put that one and this one in the denominator. Except here's the curveball. Whenever you have designated a pure liquid or a solid, if it has one of these after it or one of those after it, then you exclude it from the expression. The reason for that is because this expression is based upon concentration and the ability to change that concentration. If we have an aqueous solution like molarity, sure, you can change the concentration, just the amount of solute divided by the volume of the solution, right? But a pure liquid doesn't change concentration. And a solid doesn't change concentration. It might change equations, gases, they change concentration too. So if you have the after it can go into the calculation also. Solids and liquids, no. So that's why we only have this one in the denominator, just that. And that's characteristic of all acids. Sometimes it's written like this. There. Just like I said earlier. The shorthand version. Instead of writing the hydronium, we write the hydrogen. If it ionizes without water. And then if we do that, right, if we cover this up and make this one a hydrogen, right, then now this is the expression. Okay, so you'll see it, probably you'll see it more commonly like this than you will like that. Okay, so that's the acid dissociation constant. And we can draw the similar conclusions to the strength of an acid because we know that if it's a strong acid, it's going to be almost exclusively this side. That means very large numerator and a huge K value. Sometimes the K value is so large, we don't even report it. I mean, it's just too big to bother with. And that would be the case for things like perchloric acid, hydrochloric acid. They just, I mean, it's just stupid to try to report a number that big. And some references may do it. But if it's a weak acid, then it's going to be mostly here. This is big and that's small. So this K value is going to be much, much, much less than 1. Okay. All right. We can express the acid strength. One way to express it is percent ionization. And all that means is the value of A minus divided by the value of HA. So if we put so much of the acid in solution, and then we measure this much coming out the other side when it ionizes, this is the original concentration. This is the concentration of that after it ionizes. Then that is an expression of acid dissociation. And to make it percent, of course, you have to multiply by 100. The reason that we're introducing this topic is this value changes with the concentration. Okay, so actually, the more concentrated the acid, like the higher this value, when you first put it into solution, the higher that value, the smaller this value, acid dissociation. And it's counterintuitive, works the opposite direction. The more concentrated, the less percent dissociation. Now, that doesn't mean you have less hydrogen ions or fewer hydrogen ions in solution as you increase it, but the ratio decreases. So with something like 100% glacial acetic acid, the dissociation, might be almost immeasurable. But because it's so concentrated, even that little bit of dissociation produces a huge amount of hydrogen ions. In this case would be the acetate ion. And when it does that, then even though its dissociation is low, it's extremely corrosive. Okay. And parenthetically, there's another issue to consider. What type of acid is it? We divide acid into two groups, the organic acids and the mineral acids. The mineral acids are like the ones we described before. Hydrochloric acid, nitric acid, hydrobromic acid, they're mineral acids. Organic acids have an organic compound, is this value right here. So acetate, C2H3O2, that's an organic compound. And the reason I bring up that distinction is for safety purposes, even though you have an acid, you can't put it with some other acids. Like you don't put glacial acetic acid in the same cabinet with concentrated nitric acid or concentrated perchloric acid, because they are very strong oxidizers and they would just love to get hold of an organic molecule. So if for some reason bottles leak or break and they combine, you're going to have a violent exothermic reaction between two acids because of that organic and the oxidizing molecule get together. It's party time. I've seen it happen in the lab. Actually, it was a mistake. Some stupid technician put a chemical back into a bottle, only it was the wrong chemical. It was I think it was acetic acid he put back into a strong oxidizing acid bottle, and got a reaction. Filled the whole lab up with smoke. So all we could do until emergency arrived was outside every lab, you've got these emergency packs on the wall. We just pull one of those out and pack the door to keep the fumes out. Fortunately, the fume hood was running at the time. So once we packed the door and let the fume hood run, it would get rid of all the smoke. But it was a cleanup operation after that. I'm glad I didn't do it. I'm sorry?
What did it do to it? What did it do to the room?
Well, it was just toxic fumes. Yeah, that was the problem. Right. Even if the fumes weren't toxic in and of themselves, they expelled all the oxygen.
Oh.
It was that thick. And plus, it scattered, any acid that didn't react was blown up and scattered all over the place. Fortunately, it occurred inside the storage cabinet. So it didn't spread that far, but it was still a messy cleanup. Okay. So enough of those horror stories. The equilibrium constant for, actually, that's not true, is it? It's a base dissociation constant. Aha, I caught him in an error.
So should we fix that on here?
Yeah. Yeah, I mean, if they're gonna make a distinction between the two, they need to be consistent, right?
Yep.
Dissociation. There we go. Okay, so the base acts as a proton acceptor. So it accepts a proton from water, produces this ion and that hydroxyl. So its equilibrium constant, K sub B, because it's a base, is this one, right? We exclude the pure water, it's a liquid. So we put this one in the denominator and put these two in the numerator. And that's a constant. It's an equilibrium constant for the base when we dissolve it in water. Now, it doesn't matter what the concentration is. This equilibrium constant will be valid no matter what concentration. It's just the temperature that varies. Okay, so our previous example, this could be ammonia. And it would take a proton from water and produce ammonium and then hydroxyl. And we could write one of these expressions for it. Okay. Now, I mentioned the chemical definition of salt. Anytime you react an acid and a base, you get water and a salt. It's easiest to understand when we use an Arrhenius acid-base reaction. It's a little more complicated when we use one of those odd Bronsted-Lowry acids and bases. Oops. Okay. I must have accidentally punched the buttons.
Do you think you have an extra copy of that?
Yes. I thought, you weren't here last week, right? Okay, that's why. This is the one we did last week,
Okay,
and this is today's.
thank you.
Okay, now I can move ahead. Let's see. There's the definition of a salt. I'm not going to labor that one too much. The experiment that we're not going to get to do involves neutralization reaction, where we would have titrated an acid with a base, and we know exactly the volume of the base we're adding to it. So we can enter into a stoichiometric relationship where we can make calculations. So if we have a known concentration of base and we add a volume to it, right? Molarity times volume equals moles. We can tell exactly how many moles of base we added. So by this stoichiometry, we can say, okay, I know how much acid we have too, because they're equal. Or there's a relationship there, I should say. In this case, they're equal. In the case of the experiment we're not going to do, we would have had to do some stoichiometry. But that's a neutralization reaction where you add an acid to a base, and you always get water and a salt. In this case, the salt is muriate of potash, potassium chloride. I'm using an old word. Potash is K, and muriate is anything where chloride is added to it. You may see it at the hardware store that way. If you look at a bag of potassium chloride or potash, it may say muriate of potash on it. Or if you go to the hardware store and you need to etch your concrete, right? Clean your concrete, you can use concentrated hydrochloric acid. You just spread it out. You have big rubber boots and big gauntlet gloves on because it's and lots of free air moving because it'll choke you. But it will clean your concrete, hydrochloric acid. And it may also be called on the side of the bottle, muriatic acid. I used it in my basement once when we first moved into the house because I wanted to seal it like with a paint, spray paint on it. And I needed to prepare it first. So I used muriatic acid over there with a nice big brush and cleaned it. Then I washed it out with a hose. Then I went in with my Wagner sprayer and I sprayed it. Actually, I sprayed the wall too. Because it was over time, concrete, especially fresh concrete, will see what's the term they use. Can't remember. Produces a dust. Right? It gets all in your house, even up in the upper floors. Especially when you have a full basement like mine, you've got a lot of concrete. So I wanted to seal it. And I used muriatic acid first. Okay, so there's your acid. There's your base, there's your salt, and there's water. That is characteristic of any acid-base neutralization reaction. Now, have we done, yeah, go ahead.
We always have an acid, base, salt, and water.
Yeah, when you put an acid and a base together, you end up with a salt and water. If we do, when we were balancing equations, if we do molecular equation, complete ionic equation, and net ionic equations. Remember that? Maybe we can do that in this class, okay? If we didn't, then I won't.
I'm not so sure about the last two.
Okay, I won't digress then. It's not important for understanding this. Okay, so this is what you would see the molecule. For instance, if we have a hydronium ion that's formed from an acid and it combines itself with a hydroxyl ion, you get water. Okay, just transfer the proton. Now this proton is lost from that hydronium and produces the conjugate base, water, and the hydroxide. These are lone pair electrons here. There and there, there. The hydrogen positive comes over here and reacts with this. And now you've got H2O. And now you've got this base produces a conjugate acid. Both of them produce water. All right. Once the reaction takes place, you can't tell the difference between these two. Right? There's no way.
Did
But-
you drink it?
Yes, if it were neutral, like if you put exactly the same amount of acid and base together, it would produce nothing but water. It wouldn't taste very good because it doesn't have any minerals in it. Distilled water, they say, is just, but just, when we go in the lab, just take one of these bottles and squirt it in your mouth and see what it tastes like. It doesn't taste very well.
I'm not that brave either.
No.
Now, if you've got a jug in there, I'm not.
So, if you're going to drink water that's come from a still, you usually pass it through some sort of a filter that adds minerals to it. It tastes better. So any of these filters that you put in your on your faucet or in your refrigerator, they have the activated charcoal to absorb the chemical contaminants and microorganisms that may come through the system. And then they also have a layer of minerals, magnesium, calcium, potassium minerals. And that adds just a little bit of mineral so that it tastes good.
I tell you what, at my house, we have city water. I will not drink it, but at the farm, it's well water. And if it's hot outside, I just got two water hose and just squirt it in my mouth. But I think the well water.
It's probably cold too, but
Yes, it's very
I
cold.
would much rather drink city water than well water.
Oh, not me, no.
We had well water in our house.
I love it.
You should see what that crap does to your like bathtub, like your drains.
it depends on where it comes from. Yeah.
It was bad.
City water, like turning the faucet on and getting water. Oh, absolutely not. I will not.
They probably put a lot of chlorine in it, don't they?
Yeah.
Yeah.
But like even bottled water, I'm very picky with that. I only like off-brand water. I think it tastes better.
Okay.
I'm just picky. I'm a picky person.
It's water, and I'm picky about it.
I think I don't. Some
You don't
people,
like Perrier?
some people say all water tastes the same, but I do
And
not
that's
agree
what
with that
that's
at all.
not.
You ever see the movie Spaceballs? Mel Brooks?
That's old.
Yeah. When he's the president of the Spaceballs planet, and he opens his drawer and he pulls out this can and pops it open because they don't have any air on their planet. So he has these cans of air, and they're called Perrier. It's a green can, he pops it, and breathes air. Okay, back to chemistry again. Okay, so in a neutralization reaction, you always get water and salt. Okay? A salt, chemically speaking. Okay, this is what I was showing you earlier. The amphoteric nature of water allows it to self-ionize. In other words, we transfer a proton from, in this case, that one over here, and it produces this hydronium and the hydroxyl. And we can write an equilibrium expression for this. Right? So this is going to be a liquid, correct? This one's going to be a liquid. This will be an aqueous solution. This will be an aqueous solution. So when we write the constant for it, we have in the numerator, we have H3O plus, oops, square, and OH minus. we can't put these in the denominator. They're liquids. So this is it. That's it. Just the hydronium times hydroxyl. And this is given a special subscript, W. The KW, or self-ionizing water, is equal to, I had this one memorized, 1 times 10 to the minus 14. So it's a very, very small number. You don't have very much of this in pure water. It's there, it's measurable. But that's the KW for water. Okay, and that's your author's idea of an explanation. Oh, I didn't realize we were going to have this. Okay, there it is. In print. The important fact to take away here is not just that this occurs in pure water, but even when you put things into water, like you add an acid or you add a base, this relationship, this reaction is always there, even if you add an acid or a base. So this relationship must always be honored in any solution where you add an acid and a base or a base. Right? And that's good, actually, because if you add a certain number of acid molecules, say hydrochloric acid, which completely dissociates, right? If you say KW equals 10 to the minus 14, and that's equal to, I'm going to use the abbreviated form here, hydrogen ions and hydroxyls, like that. Then if you put, say, 10th molar, right, 0.1 molar in here of hydrochloric acid. Since hydrochloric acid dissociates completely in water, then you also know that the hydrogen ion concentration is 1/10 molar. Because this is the source, and it makes all of it into hydrogen. So the concentration of hydrogen ions is 1/10 molar. Okay, now we have an equation. We know that one, we know this one, we can solve for that one. So if 10 to the minus 14th is on this side, that's molar. Well, actually, it's not molar. I'll explain that in just a second. This one's 0.1, and this one is our unknown. Okay. So we take this one, that, and divide it into this one. So it's 10 to the minus 14 divided by 10 to the minus 1, correct? That's equal to hydroxyl ion concentration, which is equal to, let's see, this becomes a positive, so that's 10 to the minus 13 molar is hydroxyl ion concentration. Let's see, what did I skip that I was going to talk about?
The molar for the.
Oh, yeah, the K values. We never report units of measure for Ks, simply because there are too many variations, right? Remember the expression square brackets big A with the power A, square brackets big B with the power B. You can have all kinds of powers in there. And if you do the calculation, which must be applied to the units also, you could, I mean, the sky's the limit. You could have any combination of units in there. It's just too messy. So we just take extra care when we're writing these equilibrium expressions, and the value that's reported either from your calculation or that you find in reference manuals will never have units of measures with it. What it will say is, what was the source of the measure? Right? Are the concentrations in units of molarity, right? Moles per liter, okay? Or are the units in terms of partial pressures for the gases? That's valid also. So you have, say, pressure of, say, hydrogen was part of So you'd have this value in here instead of those square brackets. But I don't think we're going to get into those in this class. I'm just saying, you never put units with equilibrium constant. That's just too messy. Okay, so what do we mean by a neutral solution? A neutral solution in terms of acid base is where the hydrogen ions and the hydroxyls are equal in concentration. Now, for a, let's see, 1 times 10 to the minus 14, for a pure water situation, what will these concentrations be? If they're coming from this side to make these ions, then that one has to be equal to this one, right? Because they're coming from the same source. They're coming from a water molecule. You split it, you get the same amount of hydrogens as you do hydroxyls. So this one has to be equal to that one. So if this is x and that's x squared, then each one of these is the square root of 10 to the minus 14. So that makes this one 10 to the minus 7, and this one 10 to the minus 7. Right? That one times that one is 10 to the minus 14. So this is neutral in pure water. Okay? And if we add some acid to it, then it will make this one bigger. That one has to get smaller in order for that constant to be valid still. If we add this one, then that one has to get smaller to make that constant. So even if you take an acid and a base and you titrate them so you have exactly the same amount, if that's even possible, then you would have 10 to the minus 7th hydrogen ions, 10 to the minus 7th hydroxyl ions. No matter how much acid you start with, if you add enough base to neutralize it, we will be back to this place, always. That's what they're saying here. 10 to the minus 7th concentration of acid and base. So the neutral position is here. If you add acid, you're going to increase the amount of acid and decrease the amount of base, and vice versa. Okay. Now, this situation where we have 10 to the minus 7th and 10 to the minus 7th is valid for, I think they said 24 degrees Celsius. I think on the previous slide, 24 degrees. It's close enough to 25. The standard temperature is 25 degrees. But 24 degrees guarantees this value right here. Now, if you change the temperature, that value will change. Right? Increase the temperature, and this value will become larger, I believe. So in that case, the concentration of hydrogen ions and hydroxyls would still be equal. They would just be at higher level if the temperature is increased. If the temperature is decreased, then they go this way. So they're always equal at neutrality. For our example, 24 degrees Celsius, they're 10 to the minus 7th molar. If you introduce some acid to the solution without neutralizing it, then the hydrogen ions will exceed the hydroxyls, and that's an acidic solution. Right? It'll taste sour. If you add some base, then the hydrogen ions will decrease in concentration, and you have a basic solution.
And then that would be bitter.
And that would be bitter. Oh, yeah. Nasty taste. I bet if you take, let's see, ibuprofen maybe, and crush it and put some of that powder on your tongue, it'll be bitter.
I'm thinking it's really bitter. If you let it sit, if you let the pill sit in your mouth for too long, you
Yeah.
take a drink,
Yeah.
it's bad.
And I'm trying to remember the anatomy of the tongue. I think the bitter's toward the back, isn't it? The receptors for bitter.
Lord,
Yeah.
I don't know.
Oh, they didn't teach you that in the, wait a minute, you have to take anatomy and physiology to get that.
Wait, well, I took it, but
And they didn't talk about that? Oh,
I had it in high school too, and we did.
Never.
oh, that would be fun
I didn't even know that.
to know where the different taste buds for the receptors are on your tongue.
I didn't even know that was a thing. Thought everything tasted the same.
No, you got locations on your tongue that are more receptive to different types of taste. What is it? Sweet, sour, bitter,
It's salty one.
salty, I think. And then there's another one they call umami. That's the one that you need when you're going to the steakhouse to eat charred steak.
Yeah, I guess we had a little anatomy lesson, huh?
Okay. So if at this temperature, we have this solution that we know at equilibrium is this concentration of hydroxyls, we want to state, is that neutral, acidic, or basic? Well, let's see, 10 to the minus 4. If this is neutral, and now we're comparing with it 10 to the minus 4, have we increased or decreased hydroxyl concentration? We're less negative, so we've increased. This will be basic. Okay. How about 2 molar hydronium? That's definitely acidic, right? Because neutral is 10 to the minus 7. And 2 molar is way bigger than that. Right? So that's acidic. Okay. Let's see. Calculate. Oh, I didn't calculate these values. Right. So if we use this equilibrium expression, then we can take that value and plug it in here. Plug it in here for, let's see. Oh, we're rearranged. Excuse me. We rearranged. We're solving for this one. We already know that one, so we're solving for the other. So we leave this one here and put that one over there in the denominator. So here it is. Right? So there's the hydroxyls, there's the K value, and our calculation is 10 to the minus 10. Is the hydrogen ion concentration. So it's a lot less than 7, which makes it basic. How about the other one? Well, let's see. I'm not sure what this one was supposed to be. Is it in the? Sometimes when PowerPoint gets hold of my slides, it messes up the symbols. Here we go. Equal sign. Yeah, that's an equal sign. No, that doesn't make any sense. I'm not sure what it's supposed to be. Molar? Molar maybe? I don't know. I think it depends on the version of PowerPoint that gets hold of my slides as to whether they're up there valid or not. See, it's showing there. Anyway, we did our calculation, so we know that this is the hydrogen ion concentration, and this is the hydroxyl concentration. This one is the hydrogen ion concentration, and this is the hydroxyl concentration. No, it's not. Oh, okay. This is going to be less than. Now I see what it's trying to do.
Yeah, it's like a double less than somehow.
Yeah. Okay. And this is that way, right? Okay. Now it makes sense. That's acidic. Okay. So an acidic solution is defined as what? An aqueous solution in which the concentration of hydroxyls is higher than the hydrogen ions is higher than the hydroxyls. So the balance is shifted toward the hydrogen ions in an acidic solution. Okay. Now we know how to express molarity, even small or very large values of molarity using scientific notation, but that's still a bit cumbersome when you're going to use it day in and day out to describe solutions as either acidic or basic. So this fella, a Dane with that name, Sorensen, I'll stick with the last name, Sorensen. He proposed a modification, took the concentration of the hydrogen ions and did a mathematical transformation. He just took the log of the value. Well, let's say, what would that happen if it was neutral, -7 molar? What would the log of that value be? Remember how logs are. Base 10, right? So the value of is the exponent of 10. The log of this value is the exponent of 10 that's equal to that value. So the exponent of 10 to be that value would be -7, correct? That's the definition of logs. So that's why we use the common log, because scientific notation is going to be powers of 10 and the base of this log is 10, as opposed to natural logs where the base is e. It kind of get messy that way. So he used common log. Okay, but he didn't want negative numbers either. So that's why he did this. Just put a negative out there. Now, and he gave this a new name. He called it P, little p, big H, pH. So that's where we get the pH. You can measure it with, you can roughly measure it in with indicators, or you can get an exact measurement with a meter, pH meter. So the takeaway here is that, and typically we use a pH range of between 0 and 14. This is a mathematical transformation. You can put any number in there and do this to it. Doesn't matter. So if this is a huge number, then you may even get a negative number over here. Say we had 10 to the second power molar acid, hydrogen ions. If we take the log of that, we get what? 2. Then we take a negative, we get -2. So if your hydrogen ions are this concentrated, your pH would be -2. It's just that simple. It's a mathematical expression. Nothing special about it. See if I owe you something. I've got some papers. Go ahead.
Okay.
Yeah, if you need to take a break while I do this. Oh, maybe I don't have any. Still have some things to turn in.
Yeah.
Okay. Yeah, I probably don't have anything for you.
Do you have the last lab paper from like the last lab that we did?
Uh,
Because I was here. I didn't get it.
Osmosis analysis, is that the last one? I think so. Yeah, I should have another package.
I just asked for it last week.
Here we go. I'll edit out this dead air. Let's see. Check the time. 20 minutes until lab time. And where am I in my slides? About halfway. Okay, I don't think we're gonna make lab today. We're probably not gonna do lab today, based on how slow I'm going. But there's a lot of new concepts in this thing, and you can't go too fast, or it just all becomes a blur. Okay. So our definition of pH is a mathematical expression. Now, it does have relationship to chemistry, of course, because we're inserting concentrations of hydrogen ions to give us the pH. So the pH has to have hydrogen ions in here. But the mathematics, the log expression, I mean, it doesn't care what you stick in there.
So that's what the log buttons for our calculator.
Yeah, that's one good use for it. But since we're on that topic, and I'm glad you mentioned that. If we say we have, that's how you calculate the pH. You need the hydrogen ion concentration, and you can do that log transformation, just like this. But suppose you're given the pH, and the question is, what is the hydrogen ion concentration in molarity? Suppose you're given a pH of, let's say, and just pull something out of there, 5.4 pH. What's the hydrogen ion concentration? That's equal to negative log, like that. Now you have an equation, right? So you can't mess with this log as long as there's a negative here. So we move the negative over on this side. Now we have this expression. All right. So if we want to find this one, then the true mathematical terminology is anti-log of minus 5.4 equals hydrogen ions. But you're probably not going to find that key on your calculator. What you will find is 10 to the x. That's the anti-log key. So you need to change the sign, move that negative over here first, then punch the 10 to the x key to get this value. Now, what it means is the same thing that all logs mean. This is the power of 10 that equals that number. That's the definition of a log. That's why 10 to the x equals this value. Okay. Since we're here, I might as well do it. Complete the circle. So let's see, 5.4, and I'll change the sign, and then I'll hit my 10 to the x key. That's 3 point. I'm going to write out a bunch of decimals here and make another point while I'm at it. 3.9811. 3.9811 times 10 to the minus 6th molar. Now, how many of those can we keep? Based upon rules for significant figures, actually for logs it's different. For logs, hold on a second. Which way am I going? Backwards or forwards? If I go this direction, we can have the number of decimals here to the right of the decimal that's equal to the number of positions here. So we got 1, 2 here. We can have 3.98 times 10 to the minus 6. But when you go the other direction, you say, how many significant figures? Actually, that's not, hold on a second. Oh, I'm painting myself into another corner.
I don't like how this significant figure changes with this.
I know, well, it's the nature of the log. Right? It's not a pure add, subtract, multiply, divide situation. This is a log one we didn't cover before. Let's see. Did I put it on the slide? That would be helpful. I'm going to skip a little bit. Here we go. 5.85. pH of a solution is 5.85. What's the hydrogen ion concentration? So, right, instead of 5.4, just stick in 5.85. There we go. 1.4 times 10 to the minus 6. Okay, we can have the same number of significant figures here as we have decimals in the pH. So we have 2 decimal places here. We can have 2 significant figures there. That's the log rule. So I should say we can only have, actually we can only have 4. Right? 1 significant figure, 1 decimal place in the log.
So it's however many is half the decimal place on our.
Right. Significant figures here translates to decimal places in the pH value. I'm not going to be sticky with that one. It's just, I thought you ought to know anyway. But I'm not going to count something wrong if you got an extra decimal. Okay. Just to review, pH ranges, if it's exactly 7, that's neutral. That's what it would be for pure water at 24 degrees. If the pH is greater than 7, it's basic because of that negative sign. Remember, if we have a pH of, let's use a scale. Here's neutral. The hydrogen ion concentration, let's see, we do it out here. Hydrogen ion concentration here would be 10 to the minus 7 at neutral. Okay, we go this way and make it acid this side and basic this side. Okay, the hydrogen ion concentration will increase to the right, say 10 to the minus 6, 10 to the minus 5, on up to say 10 to the minus 1. We're getting bigger as we go to the right. To the left, the hydrogen ion concentration will decrease, minus 8, minus 9, minus 10, on down to say minus 14. Okay. So what would the equivalent pH of these be? This one would be 7, a negative log of that value. This one would be 1. This would be 5. This would be 6. So as we get smaller in pH value, we become more acidic. As we get bigger, 8, 9, 10, 14, pH, we become basic. Okay. All right. Here's some naturally occurring things. Let's see. Limes, apples are in acidic range. Grapefruit. I never thought of grapefruit being the same acidity as an apple. I guess it depends on the variety. Some apples are kind of sour and some are not. Some are sweet and sour. For some reason, those two go together. Probably has something to do with the tongue anatomy. Let's see. Butter is only slightly acidic. Eggs. What's the pH of normal blood? Did they tell you that one?
4.
Is blood acidic or basic?
You know what? This is kind of embarrassing because we learned this at the very beginning of the year.
Mhm.
Wasn't it like 6.2, 6.4?
Yeah, it was 6 something. It was like almost neutral.
So blood should be 7.35 to 7.45. Slightly basic.
Well, it's not, it's 6 point something.
Yeah, for us.
Oh, should that be 6? Let's look it
You're
up.
thinking, the diseases.
Yeah.
No.
You don't want your blood to go acidic. That'd be dangerous.
Yeah, it's 7.35 to 7.45. So it is.
Okay,
So you're thinking
Slightly
of
basic.
it being more like
Acidosis.
Yes.
Okay.
Mm.
diabetic acidosis, maybe. I saw this TV show a long time ago. You remember by name Danny Thomas? You remember Danny? Marlo Thomas, his daughter? No? He had a TV show, short-lived TV show. He played this doctor. And he was up in years when he played the part, so it's kind of fit. But he just opened a new office, and his furniture hadn't been delivered yet. And some guy came in off the street, feeling really sick. And all he had was a couple of boxes. So he set the boxes on the floor. He sat on one box, the guy sat on the other one, and he looked at him, and he leaned over, sniffed him, and says, "You need to get to the hospital." He could smell acetone on his breath. He was in extreme diabetic acidosis.
Is that called ketoacidosis?
Yes. Acetone is a ketone. He smelled that on his breath. He sent him straight to the hospital before he died. But I imagine his blood pH was pretty low. Okay. The correct expression for pH is this one. Sometimes we substitute hydrogen ion in there for the hydronium. It's the same thing. Okay. Now, since this is a log transformation, right, negative log of hydrogen ion concentrations, pH, who's to say we can't do a log transformation for hydroxyl ion values? So we do, and we call it POH. You just substitute OH in there, and you get POH instead. Okay? Or you can do it for the constant, right? You can do the same transformation for the K value and get pKa. Okay? So here's why we're introducing this topic. If you have a K, A equals, let's do it for water. It's more useful. Let's just say KW. Right? We know KW is equal to this one times this one, correct? Okay. And that's equal to 10 to the minus 14. All right. Suppose we do negative log transformation for the entire expression, all the way through. Right? Just do the whole thing. What do you get? The negative log of a KW is PKW. Okay. You stick a small p in front of it. We know this one is pH, and this one is POH. But how do they combine? All right, here's another rule from your math class. When you have x times y, and you take the log of it, the log values for x and y are now added. So the log of x plus the log of y. So this pH is now plus POH. Okay? And then that's equal to 14. Negative log of 10 to the minus 14 is 14. So now we know that pKw for water is 14. If we calculate the pH for a solution and say, let's just make something up. Say it's a pH of 5. It's slightly acidic. That means the POH has to be 9. And you can take that into the expression of POH equals negative log of the hydroxyl ion concentration. And solve for the hydroxyl. Just take the negative, let's see, -9 and do 10 to the -9 power. That'll give you this concentration. That's the simplest way to go from pH to POH, or to go from hydrogen ions to hydroxyl ion concentration, is to use this bridge. Okay, any questions about that? Didn't think you were going to get a math lesson today, did you?
Or an anatomy lesson.
Oh yeah. Well, that was a freebie. Okay, so that's what I just showed you. pKw equals pH plus POH, and that's equal to 14. Always and forever. At 24 degrees or 25 degrees, it's good enough. This will be true. Okay. Calculate pKa for HF, given that Ka is equal to 6.8 times 10 to the minus 4. Okay. Is that, do I have to write that one? Or is it going to show up on its own?
The answer will show up.
Where am I? Here we are. No, that's not even it. Well, let's see. If it doesn't give me the, there it is. Yeah, negative log of this value. And all you have to do is just punch that into your calculator and hit the log button, and then change the sign. And you got this value right here. Now see, 2 significant figures, 2 decimal places. So they did that one right. So the pK what if, okay, let's remember that value. pKa for HF is equal to 3.17. Okay, I just put that up there so I can flip slides, and now we'll still have that information. Because I think we're going to do that for, if the Ka of the solution is this, what's the pKa? Is the solution acidic or basic under standard conditions? Oh, this is not the same acid, it's a different acid. But if we have these values, and we say pKa is 3.20, should the solution be acidic or basic? Okay, in order to understand that, we need to look at this expression here, right, for our acid. And then the Ka for that one would be this times that divided by this. Okay, so if that K value is 3.2, which would be the negative log of this value, what does that say about the ratio of these two to each other? Oh, excuse me, that's not right. There, 10 to the minus 4. Okay, so at equilibrium, we're saying that it's mostly this and just a little bit of that. But can we say anything about the acidity or basicity of the solution? Like solution basic understand conditions. Ka. What's the pKa? Okay. I thought there'd be a better description. Okay. I'm trying to figure a way to explain this without getting into too technical. We know that there, with this value, that it's mostly going to be this. But is this going to produce? Yeah, this produces extra hydrogen ions, right? The KW, excuse me, KW is this one times this one. And that's equal to 10 to the minus 14. So this one says that that acid dissociates to a greater extent than water does. Right? Because this is a bigger number than that one. This one produces more hydrogen ions than the water would. And if we're just looking at the water, that's neutral. So we're adding hydrogen ions to this situation because that's 10 orders of magnitude greater than this one, right? 14 to 4. That means we're producing a lot more of these than water produces on its own. Okay. So we're saying that we're adding a lot of extra hydrogen ions. This solution would be acidic. Okay. So what would be the value here that would not change the pH of water at all? If this K value were 10 to the minus 14, it would have no effect on the KW of the water, of the acidity of the water, the solution. If it's less than that value, greater than that value, then it would start to have an impact on hydrogen ions, simply because these are competing reactions in the same solution. Okay, so what we're saying is that let me think a second. That may not be right. Let me see if I even need to beat this horse anymore. If you don't need the information, then I'm going to stop here. Let's see. I don't think you do need it. What I'm thinking is that instead of 10 to the minus 14, 10 to the minus 7. Because this one doesn't include a denominator, and this one does. So I think 10 to the minus 7 is the magic number. That would be a neutral K. Let's leave it there. I think if I go any deeper, we're going to have to start solving equilibrium problems. You don't want to do that.
Oh, no, we don't wanna do that.
And I'd have to take another hour to explain how to do that. Okay, so let's move on. So salts are ionic compounds. They form from the neutralization of an acid and a base. So you're getting the anion from one, the anion from the acid, and the cation from the base combined, and they are ionic compounds. Salts are ionic compounds. And they break up into these cations and anions in solution. It's known as hydrolysis. When you react a salt with water. And when they do that, if you just put the salt in the water, you haven't neutralized an acid and a base to get there. But say we have, let's see. Suppose we react sodium hydroxide with acetic acid. Okay. What are we going to get? We get hydrogen and hydroxyls make water, right? We got that. And then we got sodium acetate. Is the salt that's still in solution. Okay, so we got sodium ions and acetate ions. Okay, this scenario here is where we take this solid and we put it in water. Okay. So we're not talking about the neutralization reaction anymore. We're taking the salt as a consequence of this reaction, perhaps. Doesn't have to be. It's out of a bottle, solid, put it in water. Now what happens? That's where we are at this point. So when we do that, let's see, sodium acetate, and we put it in water. And what do we get? Well, we get sodium ions, and we get acetate ions reacting with water. So is sodium going to react with water? Sodium, think of where sodium would come from in a neutralization reaction. Sodium hydroxide. Sodium hydroxide is a strong base. Let's think about what that means. Strong acid, strong base. Strong acid is one that wants to give up its proton readily. It doesn't want it back. So when it gives it up, fine. Don't give it to me back. So when you take hydrochloric acid, right, it gives up its proton, says it wants to be over here. Right? So this is a strong acid. And we could say the same thing about sodium hydroxide, which is a strong base. It gave up its hydroxyl, it doesn't want it back. Right? It won't take it from anybody. So when we put this in water, is it going to react with the water molecule to get that hydroxyl back? No. It just sits there. It's a spectator. But this acetate ion, where did it come from? The acetate ion comes from this acid. And when it dissociates, it makes hydrogen ions plus acetate ions in an aqueous solution, right? Both of them. Now, where does this one want to be? It wants to be there. So the concept here is a weak acid makes a strong conjugate base. Remember the Bronsted-Lowry definition of acid and base. An acid gives up a proton, a base accepts a proton. So if it's a weak base, it doesn't want the proton back. If it's a strong base, it wants that proton. Really bad. So if this is a weak acid, it makes a strong base because it wants to be back over here. It wants to take a proton from somebody. So now that means this is a very strong Bronsted-Lowry base. So it will, in aqueous solution, it will take a proton from that water molecule. Okay, so what does it do now? If this comes from sodium acetate, now we've got this in solution, and what it tries to do is react with water, take a proton from water, make acetic acid, and what's it got left over? Hydroxyls. It took a proton, it left behind a hydroxyl. Okay? So when you put this salt back in solution, you get a basic solution. It produces hydroxyls, right? Because this is not going to dissociate any further. That ion took a proton and left a base. So now you have a basic solution when you add a salt from a strong base and a weak acid. Okay? Now, a rule of thumb is that if you have a salt that's formed from a strong base and a weak acid, you get a basic solution when you put it in water. But it's not because of the strong base source is because of the weak acid source. But the rule of thumb works. All right, if you have strong base, weak acid, salt, then it's going to make a basic solution. If you have a weak acid and a strong base, let's see, a strong acid and a weak base. So let's say, what's an example of that? Strong acid and let's see, what's a weak base? How about, can I use a mineral? No. Let's use ammonia. Strong acid, weak base. So what do we get? Well, we get ammonium chloride. There we go. Now, if we put this in solution, what's going to happen? We got the chloride ion. If we put this salt in solution, you got the chloride ion. It doesn't want a proton. Whereas this one wants to give up a proton to water. So this one, that ion reacts with water to produce ammonium plus H3O plus. So that would make an acidic solution. So if you have a salt that's derived from a strong acid and a weak base, the salt then dissolved in water makes an acidic solution. All right, I think I carried along enough with that one. Let's see what slide to go next. Let's see. Okay, the one I did leave out was if the salt is formed from a strong acid and a strong base, then you get a neutral solution. So sodium hydroxide and hydrochloric acid form table salt. If you put table salt in solution, you get a neutral solution. Acidic in terms of pH. Now, if you taste it, it's not going to taste acidic or basic. It's going to taste salty. But neither one of these ions react with water. When they go into solution here, sodium and chloride, they don't want, the sodium doesn't want a hydroxyl, and the chloride doesn't want a hydrogen. So they're just going to sit there in solution and do nothing. So water dominates. That is, the water dissociation produces a neutral solution because sodium ions and chloride ions don't interfere. Let's see. Ammonium chloride. Here we go. There was the example. Ammonium chloride. If we form ammonium hydroxide and, okay, I used ammonia. Is this going to work? That's a weak base. Yeah, that's true. It's a strong acid. Produces this salt. So in solution, yeah, there it is. That's what I wrote earlier. The ammonium ion plus water yields ammonia plus the hydrogen ions. So this is acidic solution, where the salt was formed from a weak base and a strong acid. The next one should be, yeah, there's my example. This salt is formed from a strong base and a weak acid. So we're going to have a basic solution. Okay, there it is in print. Okay. Now, what if you form a salt from a weak base and a weak acid? We didn't cover that one. Well, that's a little more problematic. It depends on which one's stronger than the other. All right, in that case, we don't have the time or the energy to deal with it right now. So just suffice it to say, when the salt has been formed from a weak acid and a weak base, that the answer is variable. It depends on the strength of the acid versus the strength of the base. So we'll let it go at that. Okay. For instance, ammonium acetate. Right? That was formed from a weak base and a weak acid. And it depends. Okay. Let's see. When salts of a strong acid and a strong base are placed in water, the resulting solution is neutral. All right, now we're going to talk about buffers. What's a buffer? Well, in chemical terms, a buffer is a solution, an aqueous solution, which will resist a change in pH when you add an acid or a base to it. Doesn't matter, whichever one. The buffered solution holds its pH pretty close. It's not fixed, it's not a constant, but it will shift only slightly. Say if you add an acid to a buffered solution, it'll only budge a little bit toward the acid side. Sometimes even if you put a lot of acid in it, depends on how you make the buffer. Or if you take that same buffer and you add some base to it, it'll only shift a little bit toward the basic side. Now, why do we want to work with buffers? I mean, why do we need to understand buffers? Because your whole body's full of them. That's why your pH, your normal pH is 7.35 to 7.45, because your blood is buffered. Now, the buffering system can get pretty complex, but it's still, the truth is there. Usually, not always, but usually, the buffering system is created by combining a weak acid with its conjugate base. So we'll stick with acetic acid. HC2H3O2 would be combined with its conjugate base. So its conjugate base would be just missing the proton, right? C2H3O2 minus. So there's the weak acid, there's its conjugate base. If we combine these two in solution in the proper proportions, we will get a buffered solution at a fixed pH. Okay, how do you do that? If you add this to solution, you don't get much of that. Right? If you just add this acid. So we have to add this in some other form. And we usually add it as the salt. Right? For instance, sodium. Add the sodium salt of this with some of that in the proper proportions, and you get a buffered solution. So in this case, we're looking at the reaction. So in solution, since sodium is a spectator, it doesn't react with anything. We're only interested in this acid and the conjugate base. So what we're looking at is an equilibrium where we have those produced and these produced. Okay? So what happens in this solution, if we've got enough of this and enough of that, and it produces some of this, and the amount of this, of course, originally will tell us what the pH is. But whatever it is, if we add acid, okay, I'm jumping the gun. Say this system is at equilibrium. Okay. What do systems do if they're happy at equilibrium? What do they do when we add something extra to them? So we add one of these, or we add that one, or we add that one. What is it going to do? That's the heart of the lab that we were supposed to do today. if you add, say, hydrogen ions, so you just add hydrochloric acid to it, right? That dissociates completely. It makes hydrogen ions. If you add hydrogen ions, extra hydrogen ions to this, what's it going to do? It's going to shift to reestablish equilibrium. And when it does that, it consumes some of those hydrogen ions, reacted with this and make that. So it's going to shift this way. Okay. But it's only going to shift until equilibrium is reestablished. Okay. So that's what happens when you add acid to a buffered solution. This strong base consumes most, but not all of it, just enough to reestablish equilibrium. So it'll consume most of those. That's why the pH doesn't change when you add an acid. Okay. You're probably thinking, all right, it's good for acid. What about base? What if we add a base to that solution? It's going to react with hydrogen ions. Right? Remember, this expression always operates in aqueous solution, always. And its equilibrium prefers to be over here because its K value is very small. Right? That means it wants to be there. So if we add hydroxyls, well, that also means if this is the acid, that's the conjugate base. If this is an extremely, extremely weak acid, that makes this massively strong base. It will latch on to any hydrogen in its vicinity. So if we add hydroxyls to this solution, that's going straight to water. Right? So what have we done? We've removed hydrogen ions from that system. Now what's it going to do? It's going to shift that way to replace some of them, right? Until it reaches equilibrium again. So when we add base, the shift is to the right, so that we replace these and retain, or pretty close to, the original pH. That's what buffer solutions do. Whether you add acid or base, it doesn't matter. The chemistry is different for each one, but the result is similar. You stabilize the pH with a buffered solution. And the key is a reaction where you have a weak acid and its conjugate base in the proper proportions. Now, as it turns out, the best buffer for a weak acid is where you have equal amounts at equilibrium of this one and that one, exactly equal amounts. Any questions? Now, we could do a discussion using a weak base and its conjugate acid, and it would be similar, but it would just take too much time, unless there's a slide on it. Okay. Let's see. Okay, this is the way your authors describe it. The buffer contains two chemical species, one that will remove the base and one that will remove the acid. And I just showed you what those were up here in terms of equilibrium. I think that's a better way to look at it than just plastering these statements on the board. All right. Let's see. So a weak acid and its conjugate base are the foundation of a buffer. Now we can say shifts to the right or shifts to the left because we have an equation to work from, right? Like I said before. You can't say left and right unless you're referencing an equation. And in the way it's written, right? Any equation can be flipped like that. Then left and right mean exactly the opposite. Okay. Well, these slides are explaining to you exactly what I put up here. If that makes more sense, fine. Otherwise, what I said there is The whole truth and nothing but the truth. Okay. Now, here's a useful equation. It was devised by these two scientists. Henderson made the first proposal. Hasselbalch added something to it, and that's why they're both given credit. So here's what happens. If this is your weak acid reaction to produce a strong conjugate base, right? We're headed toward a buffer in this case. Then this is the expression for that equilibrium expression for that acid, right? We've got the denominator, the numerator has the products, and the denominator has the undissociated acid. Okay, we're going to do some transformations here. If we want to find out what the pH is, then solve for the hydrogen ion concentration, correct? Now we want to use Sorensen's modification, his log transformation. So if we take the negative log of this side and the negative log of this side, this is going to be the negative log of H, which is the pH. Okay. This is going to be the negative log of the K, which is the pKa, correct? This, we want to leave it alone. We don't want to call this P anything. Probably because we have two terms here, the numerator and denominator. But we don't want that negative sign either. So if we have a negative log here, a negative log there, and a negative log there, we can say this pH, and notice that this negative here is, let's see, yeah, this times that. So the log transformation says this plus that. But the negative is in front of that because we're using the Sorensen transformation. So it's negative, negative, negative. So this is pH, this is pK, and this is negative log of the acid over the conjugate base. But it's a funny thing about logs. If we invert this one right here, it makes it positive. Remember that from math? Maybe. If you flip this term, that changes that sign to a positive. So that's what we're going to do. We just flip that term. Now we put the conjugate base on top and the acid on the bottom. And that makes this a positive. Now we don't have to deal with any negative signs. Okay, this is the Henderson-Hasselbalch equation. If you know the pK for your acid, your weak acid, and you know the equilibrium concentration of the conjugate base and the weak acid, then you can calculate the pH with this equation. Now, what does that mean for constructing the ideal buffer? Well, you actually need a titration curve to make sense of this. If we do that, and this is the pH on that scale, increasing, and this is, let's see, we've got a weak acid, so we're going to add base. So added base, and let's just say it's sodium hydroxide for argument's sake. So as we add more base, then we should see the pH gradually increase. Right? If it's a buffer, though, it's going to do two things. When we first start adding base, it's going to increase the pH pretty quick. But in short order, it's going to start flattening out. It's going to do like this, with very slight positive increase, until it gets to a point where this base has consumed almost all of the acid. starting to reach neutralization. Then the pH is going to jump like that. And right about in here somewhere is where the base is equal to the acid. That's the equivalent point right there. Then once we get enough base to go past that, it's going to flatten out again here like that. So notice this is the region where the pH doesn't change much. That's the buffer zone right in here. So where's the ideal position for the buffer? Where you can add acid or base and it doesn't move much. The best place is right in the middle of that zone, right here. Turns out that the best place is exactly half equivalence, or half of the base required to neutralize the acid. So what does that mean? Well, when we add the base to our acid, let's see, we add the base to our acid, it's sucking up these protons, but it's leaving this one alone. So if we add enough base to neutralize only half of the acid, we produced exactly the same amount. This is left and this is created. So they're actually equal in concentration at this position right here. So at this position, the weak acid is equal to the conjugate base in concentration. That's the perfect buffer where they're exactly equal to each other. Okay? Right. Now, what does that mean for our Henderson-Hasselbalch equation? That means that this term here is equal to that term. So when you divide this number by the same value, you get 1, don't you? What's the log of 1? What's the power of 10 that would give you 1? 0. 10 to the 0 power is 1. So this part of the term goes to 0 at the ideal buffer position. So now that means this is 0, and the ideal buffer is the pH equals the pKa. Okay? So if you know the pKa of your weak acid, you can find the ideal buffer pH. They're equal. Okay? I was trying to remember what the K is for acetic acid. I think it's in the neighborhood of 1.5 times 10 to the minus 7, I believe, something like that. So if that's the K, you take the negative log of that and you find out the ideal buffer for any acetate-based buffer. Okay. What's the pH of the solution that is 0.45 molar acetic acid and 0.85 molar sodium acetate? The K, oh, there it is, 1.8 times 10 to the minus 5. So I was wrong. It's not, it's 10 to the minus 5, not 10 to the minus 7. So there's our Henderson-Hasselbalch. We're given the equilibrium concentrations of the weak acid here and the conjugate base, right? Because sodium acetate will completely ionize in water and give you this acetate ion at that concentration. So all you have to do is plug these values into the Henderson-Hasselbalch equation. Except we have to convert this to pK. Let's see, is he going to do it? There we go. So there's the conjugate base over the weak acid. We need the negative log of the K value here. And these values, the conjugate base is that molarity of this one. Notice in this case, they're not equal. Right? So this is not going to be right in the center of the buffer zone. This is going to be off to one side. Excuse me. So if we solve this equation, we find out that pH is 5.02. The ideal, let's see, it didn't solve that equation. It didn't show us the value of the pK. 1.8 exponent 5, change the sign, and take the log of that, change the sign again. 4.74 equals the pKa for acetic acid. This will be the ideal buffer right here. So we've adjusted the pH to 5. We're going to buffer it at 5.02, which means the pH is a little higher, right? It's over here. Instead of being right in the middle, it's kind of over here a little bit. So this would be better for neutralizing acid than for base because you got more room here. You can add acid and then it'll move it back this way just a little bit. If we wanted to be better for a base, we would adjust it to a pH less than 4.74 over here. Then we could add more base to it and it'd still be in that buffer zone. That's the way I interpret it. Okay. So if you need that, let me see. Second. Okay. It's not in the test. So if you need the Henderson-Hausbach, you don't have to memorize it. Just ask me and I'll give it to you. During the test, I mean. So the expression for Henderson-Hausbach equation. Oh, that was misspelled. I forgot to delete the slide with the arrow in it. Both of these, right? Base divided by acid. What they mean here is the conjugate base of that acid. Okay, what do we mean by electrolytes? This is what's known as operationally defined. The electrolyte is any substance you put in water that will allow water then to the solution to conduct electricity. Okay. Pure water is an insulator. It will not conduct electricity unless you put something in it like table salt or a little bit of lemon juice or some kind of acid that makes ions. You cannot conduct electricity without mobile ions. So the electrolyte provides those mobile electrons and it will conduct electricity. If it's a strong electrolyte, it produces lots of ions. If it's a weak electrolyte, it only produces a few. Non-electrolytes in this system, right? Here's the solution. And here are the electrodes. So if there's nothing to conduct the current across that gap, then you get no light. Right? All electric circuits, well, they're called circuits for a reason. Circuits from the Latin that means circle. The electrons have to be able to transfer through a complete circle. Right? And if you've got a break in it here where you can't conduct, then you don't get any light. That's a non-electrolyte. For instance, table sugar is a non-conductor. Strong electrolytes gives you a bright light bulb, like strong acids, strong bases, and salts, soluble salts like sodium chloride will conduct electricity very well.
Oh, that would have been a fun one.
Huh?
That would have been a fun one.
Yeah. The fun ones are the ones that take expensive equipment. Weak electrolytes only give you a dim light like this. Weak acids, weak bases. So if you put a little bit of vinegar in your water, it'll conduct just a little bit because it's a weak acid. Okay. Let's see.
Oh, I just wanted to see where we were headed with this. Okay.
What's an equivalent of an ion? Well, there's the definition. It's the molar amount of an ion that supplies 1 mole of positive or negative charge. That's an equivalent. Okay, so 1 mole of sulfate is actually 2 equivalents because the charge is 2 minus. This is derived from acid-base chemistry, actually. So if we say we're going to react hydrochloric acid with sodium hydroxide. Okay, so that yields sodium chloride plus water. We know from stoichiometry that 1 mole of this will neutralize 1 mole of that. And the reason is it only takes 1 of those and 1 of those to make 1 of these. So they're equivalent amounts. So we could say moles of this equals moles of that. And that's true. But if we were to take this one and neutralize that one with sodium hydroxide, it would produce sodium sulfate and water. But that's not balanced. This is 2 minus charge. That's a 1 plus charge, so we need 2 of them. That means we need 2 sodiums. And we've got 2 hydroxyls and 2 hydrogens, which makes 2 waters. Okay, now the equation's balanced. All right? In this case, we can't say moles of that equals moles of that, because for every 1 mole of that, it takes 2 of these. But if we use equivalents, then we can say equivalence of that equals equivalence of this. So if we had 1 mole of this, it would actually take a 1/2 mole of that. Because a 1/2 mole of this produces a whole mole of hydrogen ions to neutralize that. Okay, so using molar, we're saying, all right, how many equivalents is this one? Well, equivalents are equal, right? They have to be equal in order to produce an equivalent on this side. So we're saying that a 1/2 mole of this actually produces 1 equivalent of hydrogen ions. And 1 mole of this produces 1 equivalent of hydroxyl ions. Because it's 1 to 1, right? 1 of these for every 1 of those. So it's 1 to 1. But for every 1 of these, or 1/2 of these, you get 2. So for every mole of this, we get 2 hydrogens, which means for 1/2, we get 1. If we have 1 here, we get 2 there. Okay, so that's where the concept of equivalence comes from. And it's useful when you're doing acid-base reactions. Then you don't have to go through a balanced equation to do your calculations. You say equivalents are equal to equivalents. Okay, so for instance, the phosphate ion right? It would produce, phosphoric acid would produce 3 equivalents for every 1 mole because it has 3 hydrogens. So that's why we say 1 mole of this produces 3 equivalents of that. It's based upon the number of hydrogens that it has as an acid. Okay, here's another concept. This would have made a whole lot more sense if I had kept the last lab where we're doing a titration. But it's the concept of milliequivalent, or actually millimolar, millimole versus milliequivalent. Okay. Milli just means 1,000th of. So if you have 1 milliequivalent, you got 1,000th of an equivalent. So if we have 1 equivalent of sulfuric acid, we have 1,000 milliequivalents. Or if we have 10 to the minus third equivalents, we have 1 milliequivalent. So what does that have to do with calculations? If we say the molar concentration of a solution is 2 molar, we know that that was derived from moles per volume or liters, right? By definition. So if we want to find out how many moles that is, we say volume times molarity. Molarity times volume equals moles. But suppose we're not measuring things in liters, right? Most often we're measuring in milliliters. So if we say, instead of that, we say milliliters per volume times molarity, we get millimoles. Because this is 1,000th of that, then this is 1,000th of that. And the same concept holds for milliequivalents. But it makes more sense for me to use millimoles to describe it. Okay. Let's see. Oh, blood plasma. Right. Have they described blood plasma to you in these terms? No. Okay.
That might be what we learn next semester in chemistry or maybe blood bank. 'Cause
Okay.
that's the 2 classes we have next semester.
Okay. Milliequivalents per liter. Right. For sodium, 138 milliequivalents per liter is normal blood plasma. So it's pretty high, actually. And potassium is kind of low. Calcium, magnesium. Sodium is the highest. So what we're saying is that this milliequivalents per liter is millimolar. Millimolar if the ion is a single charge. So millimolar and milliequivalents per liter is the same thing for sodium because it's only got 1 charge. For calcium, it's got 2 charges. So 4 milliequivalents per liter is actually 2 millimolar. Because with 2 millimolar, you get 2 charges for each one. That means the equivalents are twice as big. And the same thing for magnesium. I'm trying to think, when they report your electrolytes, they actually don't report it as milliequivalents per liter when you get your blood work back from the labs. It's usually per deciliter, I think.
Sounds about right.
Yeah, per deciliter. So this would be like 1/10 of that. It'd be 13.8 would be normal. And the only reason they do that is because if you use deciliter instead of liter, that you have more manageable number sizes. They just sort of fit better. You don't have any too small or too large. And besides, that's the way doctors learn it. That's what they expect to see. So we have to do it that way. Okay. The concentration of calcium ions present in a sample is 5.3 milliequivalents per liter. How many milligrams of calcium ions are present in 180 milliliters of sampling? This is a dimensional analysis, pure and simple. We're starting with 180 milliliters of sample. If we know this value, milliequivalents per liter, then it makes sense to convert that to liters first. And if we convert this to liters, we can cancel the liters out of this expression, and that gives us so many milliequivalents of calcium. But the ratio is 1 mole of calcium produces 2 equivalents. So there's the conversion. We have to convert the milliequivalents to equivalents. So here's the ratio of 1,000 milliequivalents to 1 equivalent. So now in this process, we've canceled the milliliters to give us liters. Now we cancel the liters to give us milliequivalents. Now we're canceling milliequivalents to give us equivalents. Now we're showing the ratio of equivalents to moles of calcium there. So now you know if you have moles of calcium, you can determine the mass. So here's the molar mass for calcium, right? Convert moles to grams. And now the question was how many milligrams? So we got to convert grams here to milligrams. And there's your answer. All right, we're going to be getting close to the end. Oh, I didn't have to do that. Sometimes I forget the animation will do it for me. Let's see.
Let's see if there are any more topics. Oh, we're going to talk about indicators and titrations.
Okay. Yeah, we're not going to get to it today. We'll do the lab after. Let's see. While discussing mixtures of ions, a chemist focuses on ion identity and amount rather than the compounds that supply the ions. So that's true. The concentration of ions is specified using the equivalent unit. Yeah. Acid-base titration. I sort of alluded to acid-base titration before when I drew that curve. Like this and then like that. A titration where acids and bases are concerned is a procedure where you're looking for your end goal is to find the equivalent amount of acid or base, whichever the unknown is. Say if your unknown amount of acid, you want to find out how much of that acid you have in moles. So you add a base to it that you do know the concentration of. So if you know the concentration of your base, say in molarity, and you know how much volume of the base you use, then that'll give you the number of moles. The number of moles of base that were used, okay, in that titration. So if you know the number of moles of base, then you need to know what's the relationship between the acid and the base in this reaction. Is it 1-to-1? Is it like sodium hydroxide and hydrochloric acid? 1 proton for every hydroxyl? Then the moles of base is equal to the moles of acid. But if the ratio is different, if the stoichiometry is different, say we had an acid with 3 protons in it, then the moles of base is going to be 3 times as much as the moles of acid. Right. If we have, let's say the acid is like this, and we're adding sodium hydroxide to it. So for every one of these, For every one of these, you need 3 of those. So we need 3 sodiums like that. No, that's not right. That's right. And then we have the waters. We have 3 waters. Okay, so now the ratio is, if you know the moles of base, it took 3 times as much base for each mole of acid. So you need, this one is now equal to divided by 3. But whatever the case may be, you can tell how many moles of acid that went into that titration by how many moles of base from this calculation. What you need is to know when you have reached the equivalence point. You could use a pH meter, right? You just measure it, right? So as you add base, then you're going to watch it like this and watch it like that. And at this point, whatever that pH is, that amount of base is here. But that's kind of take a long time. If you have 100 of those to do, and I have had 100 or more to do in one day, you need a simpler method. Okay. You need a simpler method. So that's where indicators come in. Something that'll change color when you reach that point or very close to it. So we were going to use a compound called phenolphthalein.
Is that the one you said earlier?
Yeah, turns pink, right. So it'll be clear as long as you've got acid there. But once you reach this point and you shift over to the base, start putting excess base in, then it'll change from clear to pink. And at that point, we'll tell you close enough for government work to the volume at equivalence. And you can do one after another, just as fast as you can get them going. And you can do, I can do 100 of those in an hour. If they're the same type of chemistry. If I've got the same reaction in all my samples, I got them all lined up here, then I can go through and just run them off because I know they're usually going to be approximately the same volume. So I can open, let's see, is there a picture? Yeah. I measure the volume here, and then I let volume out here. This is called a burette. You let the amount out here, you measure the difference. That's the volume I added to a solution. That's the volume of base I was adding.
So you've done 100 of those in an hour?
If I'm rushed, I'd rather take my time, but
I don't believe I want to do 100 of anything.
Anything in an hour.
You imagine.
Now,
Yes, an hour.
in middle school, when you would do like that, the multiplication chart, you'd have to, I loved those.
Oh my God.
Not me.
I had to do that my senior year of high school. I'm not even kidding. Wow. I don't know. It was awful. I wanted to leave every single day. I was over it.
I love doing
And
that.
then she failed me. I know how to do basic math. Like, ooh, sorry.
yeah, well, that's fine. It's public education is cookie cutter.
Hallelujah.
Everybody's the same. They're supposed to be the same. There's no accelerated learning, right? No such thing as magnet schools. I mean, if the left has their way. So back to our topic. So if the reaction is pretty much the same each time, right, but it's only going to vary a little bit, then you know how much you can add and get really close, right? So I set this up on a magnetic stirrer with a little magnetic bar in it so that I won't have to mix it myself. It's constantly stirring. So I know, okay. Usually what I'll do is if I have a set of 100, I'll take one sample and duplicate it, maybe another sample and duplicate that one. And then I'll run those and just find out approximately what volume it is. I might overshoot my endpoint, doesn't matter, that's a throwaway. And once I find out where the endpoint is, I can go within a couple of milliliters, I can go, and then I can slow down and get that. Okay, record that. Go do another one. Do another one. That's how you get 100 done. in an hour. Anyway, these burettes are set up so that the 0 is here, and in our case, the 50 is down here. And each one of these lines is actually a 1/10 of a milliliter. So you can measure down to a very small amount and control it with the stopcock. So you can let it, when you're very close to the endpoint where the color is going to change, then you want these to be a drop at a time. And the way you can tell is whenever this drop hits the solution, that region around that drop turns instantly pink, and then it fades away as the mixing continues. But as you get close to the endpoint, the pink persists a little longer until right at the endpoint, it changes, it doesn't change back. Okay. I forgot where I was going with this. Titrations. This is acid-base titration. The concept of titration can be used for almost any chemistry, where you have a known concentration, you add a volume to calculate how much of the unknown you have. So you can use that for all types of different chemistries. I've used it for determining chloride in a farmer's well water. So I had this kit set up with a pipette. I didn't have this fancy unit out in the field, but I could get pretty close with my kit that I carry around with me, and I could add a certain amount of silver nitrate to a solution after I acidified it and converted all the chlorine that's there into the ions. Then I could titrate it with silver nitrate, and silver nitrate produces an insoluble solid, silver chloride. That's one of the things we're going to do today. But it's hard to see, even in direct sunlight, it's hard to see that formation. So I have a color indicator in there that will react to the silver nitrate presence, silver chloride presence, and it'll turn a bright orange. So that way I could pick up the change more easily. Anyway, the titration, to make an exceedingly long story shorter, the point is titrations don't have to be acid-base. It's that equivalence that we're looking for. In the acid-base situation, it's easy to visualize the equivalence between how much acid you add to it, or how much base you add to neutralize an acid. You can do it the other way around too. That's the equivalence point, that actual point at which the solutions have been neutralized, they're equivalent. When you use a color indicator, we call that the end point. So the end point, you try to get as close to the equivalent point as possible. And within experimental error with your devices, usually you can pick a good color indicator that will get you close. Let's see, what are we doing here? All right, we're adding a little something to something else and changing colors. Okay, if you titrate sulfuric acid with sodium hydroxide, how many moles of sodium hydroxide would be required to react with 1 liter of 0.5 molar sulfuric acid? How many equivalents is 0.5 molar sulfuric acid? Equivalents per liter. This is moles per liter. Equivalents per liter would be 1 because it has 2 protons. So 1 equivalent per liter yields 1 equivalent in 1 liter. So 1 equivalent would be you need 1 equivalent of sodium hydroxide. Right? And since sodium hydroxide is 1 hydroxyl per molecule, the moles and equivalents are equal. Right? So you need 1 equivalent or 1 mole of here we go, of hydroxyls. Okay, try to sneak equivalents in there. Did that confuse? Or here's the other way you can use it. you can set up your balanced equation. Right, yields sodium sulfate 2 plus water, just like we did before. And that means we need 2 of these, we get 2 of those. So we know that for every mole of this, you need 2 moles of that. So if you have half molar times 1 liter, you have a half mole of sulfuric acid, and a half mole of sulfuric acid requires a mole of sodium hydroxide. So there you go, 1 mole. If you do this stuff day in and day out, then the equivalent can be useful. But for people like you and me, students and instructors that don't do it every day, the stoichiometry seems to work better for me. The only reason I put equivalents in there in this discussion is because you're probably going to see it again sometime, so you need to at least be exposed to it. Okay, when determining concentration of an acid or a base, blank is performed, titration is performed using an indicator to visualize the desired pH. Acid-base indicator. That field kit I was talking about was not acid-base indicator. It was specific to the presence of silver in the silver chloride. Okay, let's see. Solution containing hydronium ion concentration of this has a pH of, so we just take the negative log of that value, right? Well, it looks like they've already done it. They're all the same, so 7.03. But is that neutral? Basic? It's actually basic. But what's the hydroxide ion concentration? If this is the hydronium ion concentration, then you can do it 2 ways. You can say, okay, they've given us the pH. Negative log of this value is the pH. So what do we say? 14 is equal to pH plus POH. Right. So POH is equal to 14 minus 7.03, which is equal to 6.97, I think. Yep. So the 10 to the minus 6.97 is equal to that. Okay. How you doing? Oh, I thought you were doing calculation for me.
I wouldn't even know how to begin to put that on.
6.97, change the sign, and then hit your 10 to the X key. So that's 1.07 times 10 to the minus 7. So it'd be this one. It's slightly basic, not much, but slightly, and with that value. Wait a minute. Oh, they're saying it's so close to 7, we're saying it's neutral. Well, I guess that's all right if you round it off, but technically speaking, it's slightly basic. And that brings it up to another important topic. When the pH changes from 10 to, say, the minus 4 to, let's see, pH, to 10 to the minus 3, what does that mean for the hydrogen ion concentration? Right. This would be for, actually, it goes from 4 to 3, okay? That means this one is 10 to the minus 4 to 10 to the minus 3, correct? Okay, so what's the actual change in hydrogen ion concentration? It's a factor of 10. 1 pH unit is 10 times difference. And that's simply because of the log transformation. So this may be 1/100th of a pH change, right? But it's a significant amount of hydrogen ions that we're talking about. when you only change that much. So I take issue. I think it's basic.
This is the last one.
Okay, then I'll spend time on it. 25 milliliters of acid requires 14.8 milliliters of 0.351 molar base for complete neutralization. What's the molarity of the acid and what two products are formed after neutralization? All right. Now, the problem here is that they didn't specify. Is this a monoprotic, a diprotic, a triprotic acid? We have to assume that it's monoprotic. I mean, otherwise we can't solve the problem. All right? Okay, so if we assume that this is reacted with, well, let's just use sodium hydroxide. Then we have sodium with that anion and water. So it's 1-to-1. So in this case, we can say the moles of acid equals the moles of base. And this expression is molarity of the acid times the volume of the acid equals molarity of the base times the volume of the base. Because that's moles and that's moles. Okay. So are you laughing because it says it right there?
No, no.
Oh, okay. When my students are giggling, I wonder if my fly's undone or something. Okay, so yeah, we have to assume monoprotic and monobasic. In that case, all we have to do is, we've got an equation, we just plug in the values. So the base is going to be 0.351 molar and 14.8 milliliters of base. And then on this side, we have 25 milliliters times the molarity of the acid. And notice I didn't change these to liters. You don't have to because they're ratioed. Right? You put this one on that side, the milliliters are going to cancel. Right? So if we put this one over here, right, then we can solve for molarity of acid. Okay?
Sorry.
Oh, she's just practicing for a date. Okay, so as it turns out, the answer is 0.28 molar, 208. Okay. If this was in terms of equivalence per liter, then it wouldn't matter. Because equivalence takes into account the difference in those two. Okay, it's a good thing we're finished. Huh?